There we go. Just need to find where the mute button went. All right, let's go. Thanks, Aaron. Good evening, everyone. I'm Andrew Steingeiser. I'm the Passive House practice leader for RDH Boston, RDH Building Science Boston. My background is in architecture, and I'm also a certified Passive House consultant. RDH participated in the Stretch Energy Technical Advisor Committee with DOER for the enclosure parts of the code. I'm one of the PHMass board members among my colleagues here this evening. And I'm excited to discuss how Passive House is incorporated in the new stretch and opt-in codes and influences the rest of the code paths. So carbon reduction is now law in Massachusetts. The recently adopted Stretch Energy Code and Specialized Opt-in Code take a leap forward in decarbonizing the built environment. And we see the introduction of new metrics for buildings. As part of the updated 10th edition, as we know, of the Mass Building Code, the new base energy code includes updates to the Stretch Energy Code, as well as the addition of a second, more advanced tier of Stretch Energy Code known as the Specialized Opt-in Stretch Code. These code changes are based on the 2021 IECC with amendments. And Aaron just went over this. This map is already out of date. But the 301 municipalities out of 351 already enrolled in the stretch code, current stretch code, will continue to follow the updated stretch code July 1st. And towns, as you know, that vote to adopt the new specialized stretch code will be held to the most stringent requirements of that code. And the implementation of these more stringent requirements in both stretch codes will advance the Commonwealth's 2030 and 2050 carbon emissions reduction targets for buildings. So the code is moving towards absolute metrics rather than percentage better than approaches, as we've seen in the past. In the past, the stretch code has consisted of doing 10% better than an ASHRAE 90.1 Appendix G energy model. Through enclosure improvements like those required by TEDI and Passive House, we reduce energy loads and mechanical loads. With reduced mechanical loads, we can reduce the size and energy use of mechanical systems, therefore lowering the total EY and operational greenhouse gas emissions. And lowering the greenhouse gas emissions of the building requires less renewable resources to offset the remaining greenhouse gas emissions. So the code is now using various absolute metrics, including Passive House and TEDI. And where Passive House isn't explicitly required, the code is really modeled in other paths off Passive House requirements and practices. So all code paths are now looking at whole building performance. And Passive House is a code compliance path for all buildings, regardless of minimum requirements of other paths. Other paths implement the various elements of Passive House through multiple code requirements, kind of prescriptively throughout. This includes building enclosure improvements, airtightness, and heat recovery ventilation, all things we're familiar with in Passive House. The minimum requirements are largely based on the size and program of the building. There are 4 main paths now in the code: certified performance, consisting of HERS and Passive House, programs that you can obtain a certification in that proves compliance with the metrics of that program, targeted performance, the thermal energy demand intensity, so-called TEDI. We'll talk about that a little bit. And there's an amended version of ASHRAE still, ASHRAE 2019, with performance energy index targets versus the old percentage better than approach. Even in the ASHRAE path, there's targets that you're trying to hit. And there's a prescriptive path for smaller commercial buildings, although that is quite still stringent on its own. Passive House, again, is a code compliance path for any building of any type, and Boston, among other municipalities locally, have opted in. So all multifamily residential buildings in Boston and those other municipalities over 12,000 square feet are required to achieve Passive House certification now. I never thought I would see the day where we could say that. It's incredible for people who have been Passive House advocates for a long time to see this required in places. Passive House has the least additional requirements because of all the elements that the code strives to implement are already rolled into the standard. All the other paths try to emulate Passive House with requirements geared towards airtightness and accounting for thermal bridging. And there's a fundamental shift in the design process that is occurring. It's important to make the right decisions early. This is a common theme in Passive House, but now it's becoming important for all code paths. The new code requires early phase energy modeling to set targets that need to be followed through the design process. Early modeling allows the greatest opportunity to make design modifications with the least impact on cost. And the sort of traditional time frame for performance evaluation under the previous code cycles is kind of too late to make a difference. We want to set up that early phase energy model to set our targets, have that influence the design, and then come back and revisit that energy modeling as the design evolves through the process. The traditional ASHRAE model in late DD that sort of evaluates, where we stand with design just before permitting is no longer a viable practice. So this means we need to think a little bit about everything on day one. So again, making the right decisions early. Who does that involve day one? What are some of those examples? Just here's a couple. It involves the architect, structural engineer, MEP engineers, enclosure and energy consultants, the owner, the CM, potentially a facade fabricator, if they're going to come on for a design assist. All these decisions have to be discussed among all those parties. And, early basis of design items can be established that can then be priced out. So Passive House and Teddy. Teddy works a lot like Passive House and has the same key levers. At RDH, we talk a lot about pulling the key levers and maintaining a balanced energy budget. So some key levers can be pulled based on project priorities, and then there's a trade-off with other elements in the energy budget to maintain the balance. So in the updated Massachusetts code, most of these key levers actually have a specific minimum requirement per the Mass amendments now. And there's a list of those key levers: orientation, form, solar gains, airtightness, enclosure, thermal performance, heat recovery, ventilation. Again, all the things that we're familiar with from Passive House are also particularly important in the Teddy modeling. And Teddy is simply the thermal energy demand intensity. It's the amount of heat delivered to or removed from a space over the course of a year. It's one of those pieces of the Passive House requirements, right? We have annual and peak heating requirements. It's the annual heating requirement just on its own, with other code requirements that pick up a lot of the other Passive House pieces. So looking at these key levers, what does this mean for design? So the building's massing alone can impact how much heat is lost through the envelope. This can influence Teddy or other energy modeling before even touching the R values of the enclosure. More complex shapes or over-articulating the building massing will increase the envelope area compared to the volume. Having an efficient form factor and reducing the envelope area versus building volume will make it easier to achieve reduced heat loss. Again, something that we look at in Passive House can be applied to any building path to help achieve those particular targets. So airtightness now has minimum requirements in the code as well. The goal is to achieve modeled airtightness in the actual building as well, like with Passive House. The energy model is counting on it also. The sort of infiltration rates you can see drive results greatly in different energy modeling platforms for different paths. And again, we're familiar with this in Passive House, and it's a pass-fail criteria in Passive House. The best defense for airtightness is carefully detailing the enclosure, particularly at transitions between assemblies. Collaboration is necessary with the GC to make sure that all trades touching the enclosure are clear on airtightness priorities, and careful field observation through construction helps catch potential enclosure deficiencies. So again, much like the passive house verification or certification process, certifier process for PHI, there's fields observations that need to occur, and projects would also benefit from potentially intermittent blower door tests prior to the final to be able to identify and diagnose potential discrepancies in assemblies coming together. And so the limit in the code for all paths is 0.35 CFM per square foot of enclosure at 75 pascals. For reference, FIAS requires 0.08 versus 0.35. So the other code paths are less stringent than passive house, but the particular energy modeling for that path may dictate a requirement for airtightness beyond that code minimum to get that model for that particular path working, much like a passive house model. Heat recovery ventilation appears in the code pretty consistently now. It's important to set design targets early with the energy model. It will inform what efficiency is required of the HRV. And again, this can be held as a basis of design early in the project. There's only so much you can sometimes do with the efficiency of an ERV, right? It maxes out someplace. Passive house, we look for 84, 85% efficient ERV. Probably not going to get much more than that. So you can max out the efficiency of the ERV, but then potentially, if the efficiency of the ERV available proves problematic, you're going to have to rely on another one of those key levers a little more. So again, balancing all the elements that affect the overall energy budget. Unlike the design of the enclosure, there's only so much you could do with the efficiency. So, it's really important to look at everything at once at the beginning. Glazing systems. This is very familiar. The concepts that apply here that'll work for any code path are, again, very familiar to people working in passive house. If you choose to use a lot of glazing, it has to perform really well. You may have to be more selective about glazing design priorities. Mullions are the worst performing part. More glass and less mullions within a system will perform better than a system with many mullions. There's a requirement for prescriptively 30% max above grade wall, window wall ratio, and that doesn't include opaque doors or spandrels when you're looking at that. Most buildings will be subject to the enclosure backstop, C402.1.5. It's important to distinguish that in that backstop, the window to wall ratio there, the backstop counts spandrels, opaque or opaque glazing or metal panel as part of the glazing system, unlike the window to wall ratio in 402.4.1. So when you're looking at glazing systems, anything that's glazed in there is part of the performance of that glazed system. And the glazed wall is an FRC term. If you follow the component performance alternative, that's C402.1.5 for glazing, you should be at a pretty good starting point for your TEDI modeling or other models. But again, you have to check with the particular modeling for whatever path you're on. Again, much like passive house. The goal is to balance solar heat gain to satisfy both the heating and cooling TEDIs in that particular path. Just like in passive house, we have to satisfy our heating and cooling balanced. You drive up one, the other, you drive one down, the other one could go up. It's similar in TEDI, so this is a familiar concept as well. Code requires we be consistent in accounting for gains and losses through the enclosure, heat gains and losses through the enclosure. That includes, for fenestration, center of glass, frame, and the edge of the IGU. passive house, it also includes the psi value of the spacer instead of the edge of the IGU, and the psi install, the thermal bridging that occurs around that flanking condition around the rough opening. So it's just a matter of accounting. Passive house, as we know, takes that psi install, puts it in the whole building energy model, and accounts for it there. In the other code paths, it's also accounted for now, but it goes into derating the R value of the wall assembly, meaning when you factor that in, the R value of your assembly goes down because you're accounting for the heat transfer that goes through places like that, thermal bridges, and accounting for it, much like passive house already has been doing. So the goal is to more accurately predict performance of buildings to make them better. And we do this with enclosure performance targets. What is the heat flow when enclosure elements don't float in space? And it's a matter of counting again. How do we account for that heat flow? We use points and lines, the size and chi's, or excuse me, chi's and psi's for points and lines, and then derate that from the clear field R value or U value. So, and we also account for the interface of these assemblies. So these linear thermal bridges that occur in this middle image at the floor plate, something like that also occurs up with the parapet. When you have a transition to the wall below, between the above grade wall and the foundation wall, there's often another linear thermal bridge there. And again, those things are often factored into our passive house models, right? We'll have miscellaneous, thermal bridges that go into the Woofy passive or PHP software. So we're used to accounting for it there. Now, code and other paths are requiring us to account for it there too. For glazing, the code requires limits on the area weighted U values. And in some cases, code is requiring 3D finite analysis, i.e. the therm models we're used to seeing, the 2D therm models. In some cases, code is requiring 3D now. Anything with multiplanar heat flow, right? So if you have a section cut for your therm model and there's something beyond that influence that has heat flow going on that can't be captured if you were just to extrude that 2D cut, that's when you want the 3D thermal model. It's interesting having a conversation with FIAS, they don't necessarily require this currently, although it's a more accurate accounting for thermal bridges and clear field R value. In studies we've recently performed at RDH, we've found that a 2D versus 3D can be off by up to 50% or so, meaning the clear field R value of an assembly may actually be half of what you can get away saying it is through a 2D therm model, which again, Passive House Institute US still doesn't necessarily require. But again, it's important to be honest in your accounting of your R value and thermal bridges, so we don't have a major discrepancy between the whole building energy modeling for actual versus modeled, that so-called performance gap. If you're overly optimistic about reporting your R value in your whole building energy model, you may find that performance gap when the building's operating. So, being honest with accounting for thermal bridging and thermal performance is now written in the code as well. And the new envelope backstop, which can be avoided if using the passive house path, is simplified from the previous code versions. It looks at above grade walls and limits the ability to trade off with other building enclosure components. It only looks at above grade walls. It doesn't include the roof. It doesn't include below grade walls or under a slab. So it's really forcing performance out of the vertical enclosure. High glaze wall systems in the new code must have 100% space heating with electric heat pump space heating as well. So that's a link now in the code between enclosure and mechanical. And so there's this backstop now where you have weighted U value of the entire above grade assembly limit of 0.1285 for buildings that are less than 50% glazed, and 0.16 for buildings that are more than 50% glazed. And that may seem somewhat counterintuitive. Why would you have a higher limit for a more glazed building? Well, it's to allow for use of things like curtain wall weeds. Paul from DOER has stated that he wants to make it uncomfortable but not impossible to use curtain wall. We can still have it if we raise the limit a little bit there, and it's you're not simply going to raise the U value, raise your percentage of glazing and hit that U value and be fine, because you're going to be having more area of glazing that performs more poorly. So it's not just a matter of, oh, can I get to 51% and then get that higher limit? Well, no, the rest of your enclosure is going to be performing a little worse. And part of the requirements there, the reason those limits occur, according to Paul from DOER, are to try to help towards eliminating perimeter space heating. Having an enclosure that stands on its own performance-wise to attempt to eliminate that perimeter space heating, like we do in passive house. When we have that higher interior surface temperature on all our exterior walls, we are able to better maintain thermal comfort and potentially eliminate some of that perimeter heating. So that's part of the goal of this backstop. So again, is trying to do things like passive house is already doing, and just baking it into these requirements so all paths can try to have that mechanical advantage as well. So I looked at a case study here where we ran it through the backstop, and taking a well-performing mega panel wall assembly, ring screen assembly, utilizing thermally broken clips. Manufacturer's data has 3D modeling to determine the sort of clear field R value that you can get out of an assembly like this. So you have a good starting point oftentimes using a clip and rail system. We like this in passive house too. All the control layers are in the same plane, a place they could be managed. And when we take this wall assembly, look at the clear field R value prior to the addition of other large thermal bridges. So it's interesting again. So all these places where in the passive house modeling, you would put those thermal bridges into your whole building energy model, there's a means of accounting for those same thermal bridges now in the other paths. So when you take all the thermal bridges that occur in this case study, the R23 wall that we were looking at on the previous slide becomes more like R14.4 once you account for the thermal bridging and the heat loss through all those conditions where geometries come together and heat flow occurs. So, what can you do in this instance? You can add more insulation to the wall, or you can mitigate thermal bridges to influence your overall performance. This particular tool here is a free spreadsheet from the BC Hydro website, which is something that the new code actually references in the enclosure sections as well. And it lets you look at breaking down these thermal bridges. And this is the sort of documentation required under other code paths now. Interesting thing to note here, that 16% heat loss that's happening is from the window openings. So it's that psi install again. So, you know that you can target that now if you want to improve your clear field R value. You know what's the worst offender. So in order to obtain thermal transmittance values to plug into that previous spreadsheet tool, you can actually look at thermalenvelope.ca, the BC Hydro catalog of assemblies that Morrison Hershfield originally developed, and then BC Hydro posted it. And you can obtain some of those transmittance values now too to plug into that table. So here's an example of the weighted U value table that you then create based off of understanding your Clearfield R value after derating. So that R23 wall that started off derated with all thermal bridges, R14.4. You see in this example, this just passes the U value requirement, the weighted U value requirement. So you can do all of this. At some point, I mean, it seems like maybe Passive House is just as easy, because you end up with assemblies that are very much like Passive House assemblies, glazing that is very much like Passive House glazing. And of course, if you want to get more specific about your psi install, for instance, that worst offender thermal bridge in that spreadsheet, you could model it in Therm, like we'll often look at this in Passive House to confirm our psi install, which goes into the whole building energy model. And again, we can improve it like we do in Passive House by over insulating that window frame. What that actually does for you takes your psi install value from 0.057 to 0.022. If you go back and factor that into that table, you can figure out that just by mitigating this psi install, the flanking condition around the window openings, by over insulating like we do in Passive House, it's the equivalent to adding up to 2 inches of exterior insulation to this rain screen wall when it comes to the Clearfield R value of the wall. Again, lessons we learned from Passive House. Yeah, we can apply that here too in the other code paths. And what can you do with that? I mean, you can eliminate some thickness from your wall, gain back some runnable floor area. If you just examine early on within the accounting, which of those key levers you pull and what are the project priorities. So these kind of studies are ideally done early, like in our Passive House modeling as well. So, a whole lot of conclusions come out of this. The move to absolute metrics away from the percentage better than approach initiates meaningful carbon emissions reduction. That's what the code is striving to do now. The code is striving to lead and to decarbonize. That's the name of the game now. And beyond what ICC is doing, the mass amendments really try to step in and decarbonize. Designers may not realize what's coming with some of these backstop requirements like I just pulled out there. You're going to end up with triple glazing, warm mid spacers, 2 layers of low E, argon. It's going to be glazing akin to what you'd see in a Passive House building. So there are likely no more all curtain wall buildings for the time being, until there's perhaps some more advancement in the glazing industry towards products that can meet those thermal requirements. The 2D finite analysis to evaluate derating can be inaccurate, as we've seen, and the code is starting to recognize that. So the design phase requires accurate accounting for thermal bridging, much like we consider with Passive House, to kind of get the balance right with mechanical systems. Again, the enclosure assemblies that result look a lot like Passive House assemblies we've seen on larger scale multifamily and commercial buildings. Other benefits of Passive House include additional QA/QC. There's still currently the incentive funding for another 2 years through the Mass Save New Construction multifamily incentive. And Passive House, thanks to all these projects that have been completed, particularly here in Massachusetts, has started to have some brand recognition. Speaking with some clients, if they're going to have to do kind of similar things in other code paths to Passive House, I've heard some comments about, well, we might as well go Passive House because people recognize that and that means something. So again, benefits to potentially going with Passive House. Passive House delivers decarbonization. We've known that, and now the code has that in there through Passive House requirements, and really emulating Passive House in other code paths too. So that's what I've got there. Happy to have a discussion.
Thank you, Andrew. That was wonderful. Thanks for putting the presentation. Yeah, we'll definitely turn it over to questions now, have a discussion. You can use the chat room. You can also use the raise hand feature and ask a question directly. I'll start with one we have in the chat that came up. Andrew, can you just restate your recommendations about the use of therm modeling 2D versus 3D? It sounds like someone just had a question about which one you chose and why you recommended it.
Yeah. The code is looking for 3D modeling in cases where there's heat flow in multiple planes. If I look at this unitized curtain wall example through the spandrel conditions that are well insulated in the back pan, and then with additional warm side insulation, you can see through the heat flux diagram here, there's still in the red places where heat flow occurs and thermal bridging still occurs. So you have heat flow in multiple planes. If you cut this section here, what you're missing beyond are those vertical mullions and that intersection between these girts and those mullions. Conditions that change, the condition at the window jamb too. So in instances where there's thermal bridging in multiple planes, heat flow can go in multiple planes. That's where the code's looking for 3D finite analysis. If you've got a section cut like a mega panel wall or like a rain screen wall is much more conducive to a 2D. Let's see, where is that? Oh, okay. Something like this, you don't need to run a 3D model. This wall is the same extruded beyond, and we know how to derate for the clip and rail system. Again, that's available in product manufacturers' data. It's really, and for curtain wall, it's really at spandrels. It's at spandrels where that 3D modeling starts to become important. There's a study coming out from the Charles Pankow Foundation that I know SGH is participating in, RDH is participating in, and I think there's going to be some more guidance coming pretty soon on, in particular, spandrel conditions. So I don't know. I hope that answers the question a little bit.
Yeah, I hope it did for
yes, thank you.
Oh, great. Thanks, Erica. Yeah, so it's interesting. It seems like for meeting the code, it's really situational, depending on what's creating the thermal bridge and what you would use between 3D or 2D modeling. Curtis, do you have your hand up? Go ahead.
So Kurt Maskis, building official. First question is did I hear that 6-family buildings are going to start falling into this beyond the stretch code requirement?
Yes, so for specialized opt-in code communities, so the ones that opt into the third level of the code, beyond stretch code, okay, all multifamily buildings of 12,000 square feet or higher will be required to be Passive House.
Okay, so the super stretch code communities.
Right.
Right. Okay, so then the other observation I had, if you went back to your slide where you showed the windowsill with the extra insulation on it. All well and good that we're trying to be more energy efficient and everything, but the designers are going to have to look at how this is going to impact their water infiltration into the building. Where your slide on the left, you have a clear path for water runaway, and you're suggesting on the slide or the right part of the slide, a flat surface, and now probably relying on a caulk joint to keep infiltration from getting in between that insulation and that glazing frame.
Yeah, there's a lot of detail missing from this therm model. In reality, that actually would want to be pitched. You're right, you pitched away as well. We have details for this in a lot of our passive house projects where water management still may occur down below. There may be the sill, but then the sill is over insulated with a architectural sill above that. Yeah, no, there are. It's water management, of course, it can't be left out. We focus a lot on thermal in the passive house discussions, but of course, water management has to be there. And there are details for managing that as well. So yeah, it's something that needs to be detailed, and the design team needs to take a close look at, because it also affects the aesthetics of that window opening. So
okay, thank you.
Much to consider for sure.
Yeah. Kurt, that was a great question. Thanks for jumping in there. I mean, we look at thermal performance and air tightness. We also, of course, want to think about water control in these wall systems. Oh, go ahead, Andrew.
I mean, you're absolutely right. We don't want to forget any of the other control layers. Air, water, vapor, thermal. Yeah. We want to make sure they're all controlled.
Yeah, something we brought up in the course I was mentioning at the beginning that's coming up next week, the high performance assemblies course. One of the things we talked about in there is how to have that window installed in a way where you can have more insulation or more air sealing, but you're not covering up those gaps, or you're not covering up, say, the window weeps where some of the water can leak out. You still want to make sure that drainage potential is there. Definitely a good thing to always keep in mind. Hank, you have your question up?
Yeah, can you hear me now? Yeah. So Andrew, I know you're aware of the issues that have come up with DOER relative to TEDI and some of the modeling. A lot of people have attempted to take a passive house and model it using TEDI and find that it can't pass the TEDI requirements. And my understanding is that DOER is working through that and maybe addressing some of that in revised guidelines. Can you speak to what you know about that? It was a fairly interesting problem that came up.
Yeah, I mean, we saw this in one project we were looking at too. It was a new school, and it had a TEDI requirement of like 2.2 kb2 per square foot per year. The math that goes into this is a little different, and the energy modeling is a little different. So it's not exactly apples to apples, but by comparison, when you look at PHI, the TEDI is 4.75 kb2 per square foot per year. So 4.75 versus 2.2. Again, not apples to apples exactly, particularly with the gross square footage versus treated floor area. But that's half. That's half of what passive house would look at. And my understanding is that yes, those guidelines, those TEDI modeling guidelines, are being revised. The new guidelines are forthcoming like any day now, and theoretically make improvements in the way that the modeling is required to be done that makes it more attainable. That being said, I mean, it's going to remain just as strict as passive house modeling, and still subject to other requirements like the backstop and all the other things that you'd have to do that get eliminated in the passive house path if you were just to follow that. In those cases where you can do TEDI in the multifamily, my personal preference would be just to go passive house, because it's well established. We've been doing a lot of passive house buildings. We know how to do this. Just a personal preference. I'm a little skittish when it comes to the TEDI still, until I see those new guidelines and it's fully worked out. So passive house is a good choice because it may be equally or less stringent in some cases potentially.
Yeah, it's going to be interesting to see the new guidelines and then have folks like yourself and others run those models again to see how they stack up, passive house to Teddy. The other question I had is spandrel panels. You mentioned that, and it's something I haven't given a lot of thought to. So you're saying that the spandrel panels, if I have a window that's 5 feet, but I run a spandrel in it 2 feet down, so I get almost a floor to floor look, that the insulated spandrel panel is going to be treated as part of the window. Is that right?
Yes, your glazed system, includes the spandrel that's glazed into it.
And
as far as the backstop.
Is that an averaged insulating value? Because presumably the spandrel panel will have a greater R value because
Yes.
it will be insulated, right?
Yes. So the requirements here look at the above grade wall. If it were an all curtain wall building, your curtain wall would be subject to 0.16 between spandrel and vision glazing. And it's looking at the whole system. In addition, the backstop requires a maximum U value for vision glazing of U 0.25. That can be challenging to hit, particularly in smaller lights of glass, like an operable light that might be very small, where there's a lot of frame relative to the glazing, particularly if it's an operable light. So there are some allowances that are coming in updated guidelines as well, where that can be bumped up to 0.3, which would allow for more selection of different IGUs on the market, and accounts a little better for operable windows that might be looking at an installed U value of like closer to 0.3 or so.
Yeah. So just to clarify, I think you may have said this. The definition of the spandrel being included is that it would be installed as one unit. So you'd literally have the install would take the entire perimeter of both the spandrel and the glass. Is that right?
Yes. I mean, the side install for the opening in a case like this would go all the way around the perimeter of that glazing. The U value of that system would be the average of the spandrel and the vision glazing, with the D rating for the mullions, of course. So it's a system U value, like a whole window U value, like we do in Passive House also.
Is that implying in that case that the install is only on the outside perimeter and that's where infiltration is, and there's no infiltration within the field of those windows?
The side install is the thermal transmittance, not an air leakage. So it's looking at that the detail condition of that flanking detail for thermal bridging, not air infiltration.
Got it.
The thermal bridging of the mullions would be factored into the whole system U value of that glaze wall system.
Mm-hmm. Thank you for that clarification.
All right, folks, jump in with more questions if you have them here. We have a little bit of time to go. Andrew, I have one for you. I know you recently spoke up at in Canada at the Passive House conference in Toronto. And I know I've heard Ian reference what Canada has done with a similar TEDI kind of calculation as a basis for what Massachusetts sort of developed. So I'm sort of curious, and they also have a pretty robust passive house, network up in Canada as well.
Mm-hmm.
So I'm curious if there's any kind of takeaways that you have for how they're navigating that decision tree of TEDI or passive house, and if there's anything we can apply here now that we have a similar TEDI system along with passive house in the code.
Yeah. Well, first of all, the Canadians were blown away by the new Massachusetts code because it is potentially the most aggressive, progressive code in the United States right now. Similar things were done at first in Vancouver. There's the British Columbia Step Code, and then the city of Vancouver, has the authority to amend that further with their own requirements. And I think like the last step in the Step Code there was pretty close to a passive house level. Over time, those steps are required as code. The further steps out are required as code over time, and you can choose to follow. You can opt in to those steps beforehand on a case-by-case basis. In Massachusetts now, it's like, per municipality that's opting in. It's kind of, requiring it. But the fact that we have flipped the switch and are just requiring this now versus, even over time is even pretty aggressive compared to, say, like the BC Step Code. Teddy appears in British Columbia and Toronto. There's some little differences between how our guidelines, last I saw, were requiring the Teddy modeling here. It was a little more of a actual accounting for, you could use the same model to get your EY and Teddy out of those models. My understanding here in Massachusetts, per the last guidelines I saw, where you might actually have to have two separate models because certain things are certain inputs are prerequisites versus like more of the actual building inputs. So some slight differences between how we're doing Teddy and how they're doing Teddy, but they've been doing Teddy. It generally works. You see decarbonization happening with Teddy buildings in Canada. I hear from my colleagues in both Ontario and BC. Sorry, you get me wound up. I keep going. I hope that.
That's great. We can keep talking more about it, but we do have another question. Brett, thanks for being here. Jump on in.
Thanks, Andrew. So I don't know if it was the slide before this or the slide after this. You had a bullet point about electrification as it relates to high glazed wall systems, and I'm wondering if you could just talk a little bit more about that, when that kicks in, under what code it's required, and then I guess specifically, it's just space heating? It's not all electric. Like, I mean, obviously, I would like. Could you still use gas to heat water under that code?
Yes. I mean, it's specifically a space heating requirement. High glazed wall buildings more than 50% glazing are required to be 100% space heated by electric heat pumps. I believe there are exceptions for that. High ventilation buildings, I believe, are sized for some percentage of the peak space heating by all electric, which is a little bit funky. Grab James Peterson and talk about what that means. But, there are exceptions to that, but in general, for those high ventilation buildings, but yeah, it's space heating via heat pump when you have a high glazed building being required now.
Is it
electric heat pump?
Is it the specialized code that kicks that in, or is it the base stretch code?
Oh, let's see. I have to refer back to some of my materials.
I mean, obviously, there's other reasons to go all electric. I'm just wondering when the code is forcing it, because my understanding is it's also only if you're using a certain pathway, right? Like, there's.
Yeah, I would say it's stretch code requirement.
Right.
Mm-hmm. And I'll add in on the pathways. There is the HERS. So for residential large buildings and commercial buildings, you have different pathways: HERS, passive house, etc. When you go the HERS pathway, that's where you have that distinction between a fossil fuel building, or mixed fuel as it's called, and an all electric building. And you have the two paths. And in that case, all electric means all electric, heating, cooling, hot water, stove tops, all electric.
Thank you.
Any more spirited discussions to be had?
Wow. No, I'm not
gonna. Someone there jumping in? No, just background there. All right. It's been good questions, but this is your last call for additional ones. Jump on in if you have them. You can also just type them in the chat room if you don't want to actually speak up. That's fine too. Well, all right. Andrew, thank you so much for continuing, this conversation with us and adding to the new code and how it's impacting everything. I like this because, we talked a lot about the specialized code and the passive house aspects of that. It's nice to kind of go back and look at the updated stretch code, which is already in effect in all these different communities. And COs, is pushing us, whether you're doing a passive house building or not, to use some of these passive house principles, especially in case of these wall assemblies and envelope design systems. And I think, Andrew, you said it a few times that in many cases, just go passive house.
Yeah, that's what I'd say. And, Paul Ormond in discussions has said, in paths that didn't explicitly require passive house, passive house was modeled in these other requirements. So we know it works. We know it works towards decarbonization.
Great. Thank you so much.
Thank you.